So thank you very much to the organisers for the invitation to speak today. In this talk, I will describe some recent joint work with Okitani on plethysm coefficients, giving a recursive formula to compute a specific class of these, and then go on to discuss various applications. So this is going to be quite tangential to the main categorical themes of this conference. My background is representation theory of finite groups and algebraic combinatorics, although hopefully we'll see some objects and things that have been mentioned on the previous days. All in all, the idea is hopefully that this will be a relatively light talk to kick us off for Thursday, since we've got quite a full schedule today. And so to start things off, let me motivate what this is about. So first of all, plethysm is a kind of product of two symmetric functions. It was first introduced by Littlewood in the context of compositions of representations and general linear groups. But for today, we'll only be interested in taking plethysms of two Schur functions. So to give a definition by example, so let's say if our partition lambda is just 2, then the Schur function lambda will be x1 squared plus x2 squared plus dot 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 plus x1 x2 x1 x3 plus dot dot dot. So if we were to rewrite this just in terms of monomial symmetric functions, this is of course just m2 plus m11. And then, given another symmetric function, so let's say f, the plethysm of f with s lambda is obtained by substituting the monomials of s lambda for the variables of f. So for instance, if we take the plethysm of S2 with S2, then we can substitute in the variables to be x1 squared, x1 x2, and so on. I mean, of course, don't have to do all these spectrum. But in particular, if we write this out in terms of the monomial sums, then we get m4 plus m31 plus 2 copies of m22. The 2 copies come from being able to take x1 squared, xi squared, xj squared, as well as xi xj. And we can also rewrite this back in terms of the original Schur functions, of course. So S4 plus S22. In general, we can define this for all symmetric functions, but that's rather more complicated. This is associative of linear in the first argument, but in general, not commutative, not linear in the second argument, so I won't do it in general. But as with various different kinds of products of symmetric functions, decomposing these products gives us families of coefficients that we want to understand. So for instance, Littlewood-Richardson arises in this way, Kronecker coefficients arise in this way for the internal product, and also plethysm coefficients will be what comes out to decomposing the plethysm products. And in particular, there's still no known combinatorial rule for describing plethysm coefficients in full generality. And this open problem is problem 9 from Richard Stanley's survey on positivity problems in algebraic combinatorics. So let me just jot that down. Problem 9, Stanley is to give a combinatorial expression of plethysm coefficients indexed by, let's say, 3 partitions, mu, lambda, and mu, where this is just how many times do we see S mu in a decomposition of the plethysm S lambda with S. And very roughly speaking, there are some cases which are known. It's not known in full generality, but there are some very nice special cases which are known. And so over the last few decades, the sort of results on these plethysms have tended to come in one of a few different flavors. So some known cases, for instance, one, we can actually compute the explicit values when the parameters are quite small. So a small lambda and mu, let's say. Or if the partitions are special shapes, then there are also some results known along these lines. So I'll just say special shapes, like Foulkes partitions or special constituents. For instance, with maximals and minimals in, let's say, dominance ordering on partitions. And also 3, we can relate the coefficients to one another. So just to note down a couple of results along these lines, any lambda, mu, and mu. A very nice result of carrying the from 92. Says that the following sequence of plethysm coefficients should always be eventually constant. So what we have this sequence stabilizes, but of course it's easier to sort of visualize in terms of the Young diagrams, the parent diagrams. And so how are we growing the coefficients here? On top, we start off with our mu, and then we just add on a long bit onto the first part. And similarly downstairs, for lambda, we just add in something on to it. But then result of from 93 says that we don't actually just need to add on a long first part, we can actually do something a little bit more general, which is to add on n copies of units. So by that I mean the following sequence stabilizes as well, but more than that, it proves that it's also weakly increased. So it is weakly increasing and stabilizes. And of course here we're just adding the partition pathway. So I mean these are just two of very, very large collection of stability results and various other things that I don't quite have time to show you. But in full, problem 9 is still very much open, and the same can be said of another long-standing conjecture due to Foulkes. So, Foulkes conjecture, 1950, if n is at most n, then the plethysm of Sn with Sn, subtract the thing with m and n the other way around, this should be Scherr. So non-negative interlinear combination of Scherr. In other words, in terms of these plethysm coefficients, i.e., it's claiming the following inequality. For a slightly more representation theoretical interpretation of this conjecture, we can also phrase this in terms of regular symmetric groups and their real products. So just to note down real quick. Equivalently, this is claiming that if we take the trivial representation of Sn root Sn, and we induce it out to the larger symmetric group Sn, then this should be a sub-representation of the thing that we get when we swap. So that's the sort of rough context and setting. And what we did, so this is joint work with my summer research student, E.G. Okitani. What we did was prove a recursive formula for the class of plethysm coefficients, where the mu and lambda are arbitrary, but the mu parameter here is the trivial partition. So in particular, this encompasses those plethysm coefficients appearing in the Foulkes conjecture. But to tell you just a little bit about roughly what the formula looks like and then how we apply it, next I'm going to translate into the setting of characters of symmetric groups, just to make things a little bit easier to describe. So to set things up, here of Sn for me will just be a set of complex irreducible characters of the symmetric group Sn, and of course these are just indexed by partitions of them. And to a partition lambda of n, I'll denote the corresponding irreducible just by chi lambda. So then the Frobenius characteristic isometry allows us to translate from symmetric functions to false functions of symmetric groups. And of course, in particular, our Schur function S lambda maps exactly onto these chi lambdas. And in order to state the next couple of results about plethysm coefficients, what I'd like to do is actually phrase them in terms of so-called character deflation. These are going to be characters of certain symmetric groups, and this will just give us a slightly more compact way to describe what's coming next. So for a given n of n, let's say, if we take mu to be a partition of mn, then the sort of this so-called character deflation, which I'll denote by delta u of mu to Sn with respect to the trivial character of Sn. This is the Sn character satisfying this particular equation. So all I'm saying is the number of times we see the irreducible chi lambda in it is exactly the plethysm coefficient that we were interested in earlier. Of course, we could deflate with respect to other partitions of n as well, but for this talk, we'll just be deflating along the trivial. And in terms of these character deflations, Brion, Oriana, and Rose's proved a very nice sort of rectangular symmetry for plethysm coefficients. And I'll state it just a moment. So if we have two partitions, let's say alpha has size an for some a, and beta has size bn for some b, and in particular, they are very nice in the following sense. If I take the Young diagrams of alpha and beta, then they should interlock together to make a height n rectangle, in which case I'll call alpha and beta sort of rectangular complements. If this is the case, so if blah, 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 as drawn, so of course the width here is equals to b. If that's the case, then the deflations of alpha and beta are actually really closely related to each other. So then the deflation of alpha is just s times the deflation of beta, where s is either the trivial character of Sn, if our rectangle has even width, or it's just a sign character if our rectangle is odd width. And using this, I can state the sort of zero of case of our recursive formula. I'll write it down and sort of say a few words about why I've called it zero of case.
Does it all have a representation theory?
Yes, in the sense that we can convert this back into, I mean, this is saying something about characters of symmetrical groups. And secretly under the covers, what this is talking about, so inflation, sorry, induced inflation of characters of real products of symmetry. But sort of lots of variation under symmetrical. But okay, so the zeroth case of the recursive formula is, let's take omega to be a partition of size mn. Then the deflation of omega is simply sine times the deflation of omega plus 1 to the n. So just very, very briefly, I will say that what does this look like in terms of the original plethysm coefficients we were interested in? Equivalently, this is saying that if I take a omega lambda n, this is equal to a omega plus 1 to the n lambda prime. So lambda prime is a conjugate of lambda, of course, and then n plus 1, and this holds for all partitions lambda of n. So basically, just to wrap up, the deflations are a nice way to wrap up saying that for all lambda. But we can actually prove this. It's really sort of nice and short. So prove. First, we could as well assume that our partition omega is not too tall. If it has more than n parts, it's quite straightforward to show that the relevant deflations are actually just always the zero character. But assuming that omega only has at most n parts, then of course it fits inside a rectangle of height n. So we can draw a picture sort of like this. So omega is here somewhere, and if I pick any sufficiently large width, like mn, then of course it's going to fit. And if I consider the rectangular complement here, call that gamma, and then I take the rectangular complement of gamma inside a rectangle that's one wider, then of course what I've got here is exactly omega plus 1 to the n. So if I apply the symmetry, the rectangular symmetry twice, we get exactly what we want. Meaning the deflation of omega is sum s times the deflation of gamma, which is itself sum s times the deflation of omega plus 1 to the n. But of course, these two s's are exactly just trivial and assigned in some order because we took rectangular complements inside two rectangles, one of even width and one of one. So where s1 and s2 is trivial and assigned. So just to summarize, and also to say sort of into why I call it sort of zero case. So in general, if we take any partition of size mn, then if it has too many parts, deflation is just different. So that's saying a whole collection of plethysm coefficients. And then what we've just seen is that if nu has exactly n parts, n minus 0 parts, then that's saying that sine times the deflation of nu is just the deflation of nu hat, where nu hat is nu, but we take away its leftmost column. So we've expressed this deflation in terms of deflations of size. I mean, I guess strictly speaking, nu hat is playing the role of omega, and it should be there. But so that's n minus 0. So what's next is what if we have even fewer parts? N minus 1, n minus 2, and so on. Having said that, I'm not actually going to show you the full recursive formula in full, again, to avoid introducing too much notation, but sort of informally speaking, in a nutshell, what the recursive formula says is the following. So, nu is a partition of Mn, and we'll assume that it has exactly n minus k parts for some non-negative k. Then, sort of quote unquote, sine times the deflation of nu is some alternating sum deflations on smaller partitions, which you probably expected from the recursive nature. So just to say sort of half a line about what these smaller partitions look like, how they're related, it's really smaller partitions defined in terms of column removal, so in terms of nu hat. And sorry, this is the Richardson combinatorics. And so equivalently, this is going to be a statement for all partitions lambda of n. We're saying something about the coefficient nu lambda prime n. But of course, I mean, when we take conjugate, we still run over arbitrary. But I'll just say, so that's roughly the sort of form of the recursive formula. But what can we actually do with this? So a few sort of words on applications. So first of all, I'll sort of say 3.0, so 0, say. In terms of the form of our recursive formula or the type of the shape of plethysm coefficient that we can describe, and as I said earlier, these encompass those coefficients appearing in Foulkes conjecture. So sort of first of all we can say is, yes, we can compute some new explicit values of those. Some explicit values on plethysms of this form appearing in Foulkes. We can do this in special cases where our recursive formula admits nice enough simplifications that we can get a handle on the actual. But perhaps something that I'll say in just a little bit more detail is our formula gives us a sort of new approach to the restriction problem from general linear groups to symmetric groups in the following sense. So by this restriction problem, I mean, given an irreducible polynomial representation of GLNC, let's say lambda, what we want to do is to describe combinatorially the restriction if we take V lambda down to Sn, viewed, let's say, just the n by n permutation matrices. And so, of course, we break this down into irreducibles. We want to ask what exactly are the coefficients. There's some values coming out of whatever it is. I guess strictly speaking, I should have written the Schreck module instead of calculator. But right, so this is the restriction problem. And so, in other words, we kind of want to describe combinatorially these values here. Actually, it's very closely related to a special case of the standards problem 9. I won't describe that explicitly just now, but I'll sort of break this down further and then illustrate the connections of those. So, if we want to restrict from GLN to Sn, well, of course, in the classical angularity picture, we act on the k-fold tense product of the natural module. On this side, we get an SK action, and for Sn, on the other side, we would have the partition algebra. And so to break down this restriction into steps, what I actually want to introduce is a sort of intermediate centralizer pair. Namely, here we'll have the complex reflection group GR1N. So abstractly, it's just a nice, easy brief product. It's cyclic R brief Sn. Explicitly, you can think of it in terms of n by n binomial matrices where all the non-zero entries are R roots of unity. So of course, the Sn case down there is just a case of R equals 1. And on the other side,
So R doesn't relate to K.
Sorry.
R doesn't relate to K.
I can't remember whether you do actually need R greater than or equal to K or something, but if so, that would probably be a restriction. But on the other side, then what do we have here? We have UK, which is my notation called a uniform block permutation algebra, also known as the party algebra, for a reason that I'll explain in sort of 20 seconds time. But so it says this is sitting inside partitions. Let me just sort of very quickly describe what UK is in terms of the usual diagrammatics. So if we take so, for instance, if we're just taking set partitions of 2k points, sort of k on top, k on the bottom as usual, then the allowable diagrams inside the party algebra have to, each part of the set partition has to involve the same number of top vertices and bottom vertices, hence the sort of uniform. So for example, let's say here we've got one top and one bottom, and then two on top, two on the bottom, and then let's say three. What happened? That one, and then two and two. So in particular, when we vertically compose these, of course, we don't actually get any loops, which is why the parameter n has disappeared. And okay, so as promised, why is it a party element? It's actually not a fun kind of party. It's sort of originally representatives of political parties sitting down to meetings with equal numbers of people. Anyway, fine. Catchy name party. So, okay, where were we going with this? We were saying restriction problem, we can break it down into two steps. So to go from GLN down to SN, then we can say, okay, we'll just go GLN down to the complex reflection group first, and then complex reflection group down to SN. On the other side of the picture, that's just partition down to UK first, and then UK down to SN. Now, why does this help? Well, for the sort of group product here down to SN, or equivalent partition down to UK, that's actually just relatively nice and straightforward. It's Littlewood-Richardson. So this part here is just governed by Littlewood-Richardson coefficients. So really the bulk of the problem is what happens when we restrict from UK down to SK. And so in a very recent paper of Orellana, Saliola, Schilling, and Zabocki, they calculated all of the characters of UK and also basically drew some immediate connections between this and that. So, so computed characters of UK, and in particular, let me just very quickly jot down an indexing set for the irreducible. So these are indexed by tuples of partitions. The tuples themselves aren't very hard to describe at all. So here, lambda back, it's just a sequence of k many partitions such that the following weighted sum, so I times the size of the ith bit, such that this is k. And in particular, they show that if we take this irreducible and we restrict down from UK to SK, then okay, we get some general expression with some general coefficients, like so. So I'm running out of names here, but we get some restriction coefficients, these B's now. But the point is, where B, mu, lambda is the following expressions in terms of looking at constituents of products of symmetric functions. So we're looking at how many times S mu appears in the following product. So how to multiply out the brackets with each other, that's just Littlewood-Richardson again. And what about within each bracket? Within each bracket, it's just a kind of plethysm, but a very special kind of plethysm, where on the right, we're just looking at S sub a trivial partition. So all in all, the point is to say, they observe that for the restriction problem, it is somehow enough to understand the special case of how we decompose plethysms of the sort where we have S sub some arbitrary lambda, plethysm S sub some arbitrary trivial of some size, and then we just want to look for its constituents. But of course, this is exactly a new lambda n, which is what our formula gives sort of recursive way to describe. And so this sort of gives us a new framework for tackling the restriction. So that was 3.1, there's a 3.2 at its time. But okay, so
where's the R?
where's the
R. CR.
so you can actually vary R, so in some sense, so long as it's probably greater than 15 or something, it's not actually relevant what R is. I'm not entirely sure. This is about as much as I have known of the uniform. But I could probably give you the reference. But what was I going to say next? Well, okay, given that kind of representation theorists looking at finite groups, I should probably say something about applications to that domain as well. So 3.2 is exactly that. So some key questions that we can ask are, of course, how do we relate the representation theory of a finite group G with that of its local subgroups? So local meaning non-trivial P subgroups, that normalizes, that centralizes, things like that, and sort of local global theory. And something else that we can also ask is, of course, what do irreducible characters actually tell us about group structure? So for C-law subgroups of finite groups, there's actually a nice sort of recurring pattern of results that I can write down. So here G is any finite group, P and prime, and I'll let capital P denote a C-law P subgroup of G. Then the nice pattern is the following. So our C-law subgroup satisfies some algebraic property if and only if the prime P does not divide the character degree chi of 1 for all chi coming from some subset of the irreducible characters of G. So a sort of nice classical result of Ito and Mischler to describe exactly when a C-law subgroup is both abelian and normal. So here the sort of algebraic property is normal in G and abelian, and they show that this happens if and only if all the chi of 1s for all of our irreducible characters, all of them are prime P. So the sum subset here is really just the whole of the G. And so naturally it's kind of nice to say, can we actually separate these two conditions into some subset that characterize normality and some subset that characterize abelian? And the answer is yes, as of rather recently. So due to Mala and Navarro, keeping abelian corresponds to the subset that is the principal P block group. And actually this is a special case of our zero conjecture, which is no longer a conjecture, as of sort of like a couple of points ago, it's finally solved it. That's sort of the story. So that's abelian. And what about normality? So also Mala and Navarro in 2012 P is normal in G. This is described by the subset of irreducible characters satisfying the following. So Z chi1 is positive, where, let me give myself a bit more space. Z chi1 well, positive, where this is simply the multiplicity with which we see chi as an irreducible constituent of this perfect character here, trivial repeated stuff. And in recent joint work with,
like if you want to have satisfy two properties at the same time, won't you take the intersection?
Sure. This one sort of came in the 50s. So for a long time, people were trying to separate each other. I mean, this was predicted very early on. Yeah,
I guess I'm just confused. Like when you have both of them, you. Oh, I'm sorry. Yeah. Okay, I'm fine.
Sorry, I lost my mind. Sure. So yes, having split these two, the next one is actually just another characterization of when the C-model is not formed. And so in joint work with Gianelli, Jason Long, and Carolina May, then we show that P being normal is characterized by, I mean, there's these same multiplicities Z, but now just looking at the divisibility properties rather than the positivity properties. So in other words, this normality property is controlled by this even smaller subset. And where's this time to that? So again, thinking back to the characteristic by symmetry, that allows us to translate between plethysms and characters of symmetric groups and new products. And so our formula gives new information on these multiplicities in the case of, for instance, symmetric groups, because their C-log subgroups are exactly the one. So a lot of details under the covers, but the point is that by knowing something about plethysms, we know something about reproductive symmetric groups, and that ties into looking at these coefficients, and we can start to get a handle on exactly which chi it is that these properties. And finally, I promised something else in the title, which was stability. So the last little bit will just be a bit, will just be some words on stability properties. All right, so given your favorite partitions lambda and mu, I want to consider the following sequence of plethysm coefficients. If I want a sequence, then I need to grow my partitions in some way. So how I'm going to grow these partitions is to define lambda sub j, and I write this out just in terms of pictures, easier than sort of writing out the actual formal notation. But if we take the Young diagram of lambda, all I'm going to do is add on j many parts of size 1 down. So we'll just concatenate on j many ones, and we'll define new upper j. So we'll add j down the bottom as well, but we'll also add on j into the first part. So on sort of downstairs, we sort of add on some legs sort of thing, and upstairs we sort of put an arm and a leg. Now, why are we interested in these coefficients? a recent conjecture due to Bessenrot, Bowman, and Cadman. Is that sequences of plethysm coefficients that grow exactly in this form, with parameter and the trivial partition of 2 down here, these should be weakly increasing for all lambda and b. So we're not able to prove the monotonicity conjecture. Looking back at our work, I did show you, but thinking back to the sort of nutshell description of the recursive formula, it's an alternating sum, there are signs, and the signs have made it harder to get a grip on sort of inequalities. But what we can do instead is actually show that these sequences are eventually constant. So I'll say proposition these stabilizers for all lambda. We can go a little bit further than that. So here we just have 2, but we can generalize that to arbitrary natural numbers m in the following way. So then this stabilizes where I'm actually going to change the definition of mu j and lambda j because somehow the growth should depend on the parameter m. So where actually lambda j is the same as before. So lambda sub j, we just add a label length j sort of down the bottom, and mu j now growth. The dependency on m is exactly in how much we add onto the first growth. So that part's the m minus 1 times j. And of course, the line above is the case of m. So having said that, we can actually go a bit further still. So the next generalization will involve a few more pictures. So still for arbitrary lambda and mu, but what I would like to consider next is the following sort of infinite triangle, being infinite, let me just draw the first few rows of it. So they will be indexed as follows. So what do all of these entries represent? So given a row n, so n is going to be my row index here, and L will be my column index. So across this way, that's L. Then ALM represents a sequence of plethysm coefficients, namely okay, so I promise this is actually the last time that I will redefine mu j and lambda j. The point is just so that I don't have to carry around superscripts and subscripts and so on. But so for the last time, what is the current definition of mu j and lambda j? So where I just sort of squeeze it into the bottom here, mu upper j now. Well, before we were sort of adding on one arm and one leg. Now I will add on one sort of long arm of length Lj, but I will add on lots of legs. So n minus L many legs of length j. And lambda sub j, this is either going to be adding on and on, or length, depending on the parity of n plus L. But okay, so the point is these are sort of an even more general family of plethysm coefficients that grow in some particular way. But what's the point of this triangle here? Let me summarize some of the stability results that we've just been chatting about. So to mark this on, let's say in yellow or orange or whatever this nice color is. So if we look at row 1, when m equals 1, actually these plethysm coefficients are just always constant because they just depend whether nu itself is equal to lambda. The point is to say A01 certainly stabilizes, I'll put it down as a tick because it's just a constant sequence. And similarly, A11 is also constant. So those two stabilize. And if you think back to the earlier results of Karen and Tubbenhauer and Brion that I wrote up several boards ago somewhere, then that would actually tell us that when L equals M, so when we're along this top edge of the triangle, we also get stability. So I'll just say CT means Karen and Tubbenhauer and Brion. Then we get ticks all along this diagonal. Dot, dot, dot. And there's a nice involution that we can apply to sort of conjugate partitions. And if we do that, actually we get, so not the far side of the triangle, but the near side here, L equals 0, also stabilizes as a result of Brion's result. I'll sort of say B prime because we secretly conjugated. But okay. So we've sort of got the outside edges of the triangle, so what's there? Our proposition on the sort of left-hand board there is exactly the case of A12. So I'll say 2, we now know that that stabilizes. And in fact, the sort of lower generalization over there is exactly this sort of sub-diagonal, L equals N minus 1. So we put ticks all down this sub-diagonal as well. And now, okay, what do we expect next? What happens to the rest of the triangle? And yes, it all stabilizes. So that's sort of no real surprise there. So I'll just say, so write it down here. So just to record, theorem ALM indeed stabilizes for all L and M and lambda and mu. In particular, it actually holds for skew shapes as well, not just genuine partitions, just input stability of the bridges as well. And then now that we know things stabilize, we can ask further questions like, what are the limit values? Or in here, we've just been dealing with a trivial partition of n the whole time. What happens if we generalize that to other partitions of n as well? But just to wrap up, last 15 seconds, where did this all come from? This all came from the original conjecture of Stacey and on weakly increasing. So just to weakly decreasing, just to record what we know about that situation so far. Well, okay, of course, constant sequences tick. And then the earlier result of Brion said not just stability, but also weakly increasing as well. So everywhere where we see a B, we can also put ticks there, and now we know monotonic 2. So down the far side and down the near side. Right. And so on the inside of the triangle, the A12 case is exactly what was conjectured by BVP. And that's still open, so I'll put it as a question mark. And so this is the final little thing that this code suggests is what happens to the rest. And the natural guess, conjecture, this should be weakly increasing. for all L, M, lambda, n. And on that note,